get started. Our next talk is on lunar craterology using remote sensing data from Chandrayaan missions from Mangala Bugge. So you may go ahead and get started.
And I'm going to mute the room.
Okay. Okay. Good morning, everybody. Thank you for this opportunity from the Planetary Crater Consortium to present a bit of our work here. And it's great connecting with all of you. And this is my first time interacting in LPI meeting like this. And I'm Mangalamani Bugge from India. And I'm a research scholar, basically working on planetary data, the moon specifically. And my guide is Professor Wazir Muhammad, who has been encouraging me and supporting me to carry on this work. And we are from Andhra University, College of Engineering, Visakhapatnam, AP, India. Now, yeah. My topic for today is the lunar craterology using remote sensing data from Chandrayaan missions. So there's a lot of research going on lunar surface by different countries, and USA started right in 60s, and it has been continuing, though there was a small break between, but most of the nations are working on planetary sciences. And of course, even India, we have our own missions, the Chandrayaan 1, 2, and 3. And there are future missions also which are going to come up. So basically using this Chandrayaan data, we would like to present our work which has been carried out on some of the craters here. So this is the Moontrek base map which we have downloaded, and there are about 4 locations which we have selected for our study. One is in the North Pole region, and 2 of them are in the equatorial region towards the south, and then one is in the South Pole region. Oh, 1 minute, I'm trying to get this thing out of my way, the side panel, yeah. Sorry for that interruption. I was having the side panel and it was interrupting my view of my presenting slides. Sorry about that. Okay. So these are the 4 locations on the lunar surface which we have chosen for the craters. 2 are in the polar region and 2 from the equatorial region. One is from the North Pole, that is Hermite A. And then the second one is Wurzelbach C. And the third crater we have selected was Clavius D. And then the 4th one is Boguslawski. So the Chandrayaan data which we have used for these things were, one is for the Wurzelbach C. We did a study of serenomorphology, the crater, actually the depth of the crater, the width of the crater, the rims and ejecta, and also studies using the terrain mapping camera. Terrain mapping camera is a triplet, which means it has a 4 camera, an aft camera, and a nadir camera. So this is basically a 5-meter resolution, and it's a panchromatic covering the range of 0.5 to 0.85 micrometers spectra. And this is basically meant for generating stereo maps. And this is the objective of this camera is to map the lunar surface topographically and generate a DEM out of it. So whatever DEM was generated by this TMC, that has been used as a reference, and we have selected this particular crater which has different morphological features and worked on that. And the second crater, petrology, Clavius D, was used to study the petrology, the rock formation or the rock type of rock from the sensor imaging infrared sensor spectrometer, that is IIRS. It's a hyperspectral sensor, and the spectral ranges from 0.8 to 5 micrometers with a 80-meter resolution. So these resolutions are pretty good, and we can finally study the fine features of the rocks here. And for the Boguslawski crater, actually the Chandrayaan data comes in strips, and we have mosaic this one particular crater to study the whole crater as a lot. And then we did a study of mineralogy on this. For this, we have used the Moon Mineralogy Mapper, which has flown on Chandrayaan-2, developed by NASA. And this has a spectral range from 0.7 to 3 micrometers with a resolution of 70 meters for in a targeted mode and 140 meters in global mode. So in global mode, the spectral bands would be 86. And finally, we have chosen one more crater in the North Pole region, Hermite A. And for this crater study, we wanted to do some hydroxyl studies using the SAR data, synthetic aperture data. And Chandrayaan-2 had a dual frequency synthetic aperture radar, which we intended to use, which has both L-band and S-band. So we took a product of L-band data, the full pole data, and worked on it, whose resolutions, the range resolution is from 2 to 75 meters, and with an inclination angles of 9 to 35 degrees, which are useful for such studies. Okay, moving on. So the cellomorphology studies on Wurzelberg. I don't know if I'm spelling it properly. Wurzelberg C. So this is the total crater, and specifically by using the DEM, we have followed the method of descriptive index system and also the depth to diameter system method to arrive the depth and the width and all of the details of morphology. And yeah, this is the DEM image over which we have taken the profile of Wurzelberg C crater. So you can see the depth of the crater is about 1.8 kilometers from the surface, and its rim slightly raised up only up to 280 meters, and the width is almost 20 kilometers if we take this FWMH width. Next, we have the petrology, the Clavius D, and here we have used the IIRS data. And to characterize this crater, we have used the method called spectral angle mapper. This is a technique which uses the hyperspectral data for every pixel. This calculates the the pixel value is calculated, and into which spectra does it fit across all the bands. So that is mapped with the existing library spectrum, and then we are given the output. So for this spectral angle mapper, we have taken the JHU library, John Hopkins University's spectral library, the rock spectrum, the library of JHU, and then tried mapping the pixels with that library. So the output we got was the mafic basalts, H2, H10, and the ultramafic pyrite H2. These are basically the levels of silicates in that rock content. The H2, H10 indicate that figure. And mostly these are mafic basalt rocks having high content of iron and magnesium. And we can also see the red spectrum. In the red one is the basalt indicated, and the green one is from the actual data which we got, which are matching. The pattern is matching. Next, we have the mineralogy. Like I said, we have to mosaic 4 strips of M3 data to get this whole crater. And for this also, again, we have used the same spectral angle mapper, but this time we use the spectral library, the mineral library of Relab as a reference. And again, the output we got was mostly, it was Olivian, as you can see from the image. And some pixels were classified as plagioclase and other volatile elements like ilmenite and a few others. So here also we can see the spectrum of M3 data, the reflectance from the crater. Mostly it's all this purple indicates Olivian, and the spectra of Olivian, and also the spectrum from the library. Both the profiles of Olivian and ilmenite are shown here. Next, we did some hydrological studies, hydroxyl studies on crater in the North Pole region, Hermite A, using the microwave data. That is the DFSAR, dual frequency synthetic aperture radar data, taking the L-band data which was available at that crater. And we use the methods, decomposition and sigma naught methods. And the sigma naught values which we got were very high. The HH for all the different polarizations, HH, HV, VH, and VB. This suggests the presence of very rough terrain. And also, when compared with the other literatures, we could find some signatures which match, suggesting that they are icy bodies.
Just to let you know, you have 2 minutes remaining.
Yeah. Thank you. So I'm almost done. I'm complete. So in summary, the TMC data, which was used both from Chandrayaan-1 and Chandrayaan-2, also provides clue for smooth evolution of the crater formation process and helps us prepare 3D maps of the lunar surface. This camera enables in preparing global high-resolution imaging mosaics, because we have this particular camera is 5 meters of resolution and DEM is 10 meters resolution, and this was comparable with the Lola DEM also. And then the Chandrayaan-2 IARS data, this has identified the rocks which with rich iron and magnesium contents. And Chandrayaan-1 again, M3 data yielded results indicating that lunar surface is primarily composed of mostly Olivian pyrox in the mafic minerals, and to a lesser extent has plagioclase feldspars, the felsic minerals, and other volatiles too. And Chandrayaan-1 instruments detected the presence of hydroxyls and water molecules on lunar surface using M3 data, and also lunar exosphere using CASH instrument on the Lunar Impact Probe, and a subsurface water ice deposits in the base of craters of permanently shadowed regions using MINISAR of the NASA. And in our study too, we yielded similar findings using the DFSAR instrument on Chandrayaan-2, and that these areas in the North Pole might have thicker ice layers, larger ice grains, or be contaminated with impurities. And yeah, to conclude, we have used the Chandrayaan data, which is still available on the ISS DC portal, and Chandrayaan-2 is still sending data, which is launched in 2019, and Chandrayaan-3 data also. This it becomes important because it's like an in situ data which we have, and we intend to compare these results for mineralogy in the future work. So lunar cratology is in understanding the moon's formation evolution, and unambiguous identification of potential moon resources like water ice, minerals, volatiles, etc. Using advanced methods on Chandrayaan data, which is of high resolution and high spectral and spatial resolutions. So way forward, there are some
I think I'm gonna
things.
have to stop you so that we can
Yes.
stay on time for our next speaker, but let's thank the speaker very much.
Yeah. So this is the way forward. Thank you so much for your kindness.
Thank you.
Thank you.